The next thing we'd like to use to measure vector fields is curl. And curl measures rotation. It's going to behave slightly differently in 2D and in 3D because rotation is a more complicated concept in 3 dimensions. When we're working in 2D, we have what's called scalar curl. At each position, scalar curl measures how fast the vector field is rotating. So if we've got some vector field that moves in different directions at different places, we can see how fast it's kind of rotating an object that's stuck at that position and can't move but can spin. So there's a formula for the curl. What we do is if our vector field has a first component p and a second component q, and we take the derivative of q with respect to x minus the derivative of p with respect to y. And if you like, you can write this as a determinant, where in the first row we put the gradient object, nabla, or del, or whatever you like to call it. And in the second row, we put the vector field f, and then we take the determinant. So that's a shorthand method to remember it if you don't like remembering this formula. And the way curl is measured is that if curl is positive, we rotate counterclockwise, and if curl is negative, we rotate clockwise. This is according to the right hand rule. If you take your hand and you plant it down on top of the vector field, it should curl from the base of your hand around your fingers, measured with your right hand, like so. So here are two examples. This function f of xy is equal to x comma y on the left. This example we saw from the first part of today's lecture. If I take the partial derivatives to calculate curl, I'm taking the partial derivative of y with respect to x for the second component minus the partial derivative of x with respect to y, and that gives me curl 0. This vector field isn't actually going to spin you. If you're stuck at a particular position, it just kind of pushes you straight, and it doesn't change your rotation, doesn't impart any angular component when it's trying to move you. By contrast, this other vector field, f of xy is equal to minus y comma x, this looks more like something that does rotation. And we can measure that by taking the curl, the derivative of the second component with respect to x, minus the derivative of the first component with respect to y, and that gives me an answer of 2. 2 means that it's rotating things counterclockwise, and the rotation doesn't depend on where we are. It's always giving us the number 2, so it's kind of giving us a constant amount of rotation, no matter where we are inside space. So it's not too bad to calculate scalar curl, and it gives us this information pretty straight up. When we do curl in 3D, it's a little more complicated. In 3D, the curl of a vector field assigns a vector at each point. Instead of just measuring rotation, it has to tell us also how we rotate. When we take the curl, at each position it tells us a vector. The length of that vector tells us how fast we're rotating. And the direction of that vector tells us the axis of rotation, and it follows a right-hand rule. So if the curl vector is a vector out here, if we put our hand inside three-dimensional space, our right hand, and point our thumb along the curl vector, the vector field is rotating in the same way as we saw for scalar curl. From the base of our hand around the tip of our fingers is the direction of rotation of the vector field. So that's how 3D curl works, and it has a formula. There's a formula that I can write down. Here it is. We don't usually remember it that way. It's much handier to have a shorthand notation for the rotation. And curl we write as grad cross f. So just like divergence was grad dot f, where we take the components and multiply them together, here we take the vector del like this, and we take the vector field f, and we imagine we're taking their cross product. So we put the vector del del x, del del y, del del z in the first row, and we put PQR in the second row, and then we take the determinant that we get by adding ij and k to the top. So that's how three-dimensional curl is calculated. So if we were to take an example, let's calculate the curl of the vector field 2y 2y, 2y, like so. If we were to calculate this, we would write down ijk, del del x, del del y, del del z, 2y, 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 and so on. And then we get the first derivative is the y derivative of 2y minus the z derivative of 2y. That's just 2. The next one is minus j, the z derivative of 2y minus the x derivative of 2y is 0. And finally, k, the x derivative of 2y minus the y derivative of 2y is minus 2. So the three-dimensional curl of this particular vector field is 2, 0, minus 2. And so if we were to take our hand and point it so that our right hand, so that our thumb points in the direction of this vector 2, 0, minus 2, that would tell us exactly what direction this particular vector field is spinning.